Quantum physics, a branch of science that delves into the mysterious and perplexing realm of the very small, has consistently defied classical intuitions and challenged our understanding of the nature of reality. At the heart of this enigma lies the concept of observation, an integral and often baffling aspect of quantum mechanics. This article seeks to explore why an observer is a critical part of quantum physics, delve into the meaning of being an observer, investigate whether the act of observation affects the external world, and unravel the persisting mystery surrounding observation in the quantum realm. In classical physics, the idea of an observer influencing the observed object seems absurd and counterintuitive. However, in the quantum world, the observer plays a crucial role, not merely as a passive spectator but as an active participant shaping the very fabric of reality. This distinctive feature is encapsulated in the famous thought experiment known as the Double-Slit Experiment. The Double-Slit Experiment, first conducted by Thomas Young in the early 19th century and later refined with electrons by Clinton Davison and Lester Germer in 1927, is a cornerstone in quantum physics. In this experiment, particles, such as electrons or photons, are fired one at a time towards a barrier with two slits. The surprising result is an interference pattern on the screen behind the barrier, as if the particles were behaving as waves. However, the most perplexing aspect arises when we attempt to determine through which slit a particle passes. The moment we introduce a measuring device to observe the particle's trajectory, the interference pattern disappears, and particles behave like classical particles, exhibiting a particle-like pattern on the screen. This apparent alteration in behavior due to observation poses a fundamental question: what is the role of the observer in influencing the outcome of quantum events? In quantum physics, the term observer extends beyond a conscious human observer to any measuring device or interaction that extracts information from a quantum system. This implies that the act of observation is not limited to sentient beings but encompasses the broader concept of measurement. The observer is intricately tied to the collapse of the wave function, a phenomenon describing the transition of a quantum system from a superposition of states to a definite state upon measurement. The act of measurement forces the system into a specific state, effectively collapsing the probabilistic nature of quantum states into a concrete reality. The question then arises: what triggers this collapse, and how does the observer play a role in this transformation? One of the most intriguing aspects of quantum physics is the apparent connection between the act of observation and the behavior of particles. The double-slit experiment exemplifies how the act of observation can fundamentally alter the outcome, suggesting that the observer's influence extends beyond the realm of classical physics. This phenomenon has led to various interpretations of quantum mechanics. The Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, asserts that observation is an essential component of quantum reality. According to this interpretation, quantum systems exist in a superposition of states until observed, at which point the observer's interaction forces the system to choose a definite state. Despite the advancements in quantum physics, the nature of observation and its implications on reality remain shrouded in mystery. The quantum measurement problem encapsulates the inherent paradoxes and unanswered questions surrounding the act of observation in the quantum world. One key challenge is understanding how an observation made in one part of the universe seemingly instantaneously influences the state of a particle in a distant location. This apparent violation of the speed of light constraint, known as quantum entanglement, underscores the need for a more comprehensive understanding of the relationship between observation and the external world. The connection between consciousness and observation in quantum physics has sparked philosophical debates and raised profound questions about the nature of reality. The idea that consciousness plays a role in the collapse of the wave function is often associated with the mind-boggling implications of the observer effect. Some argue that consciousness is an integral part of the quantum world, influencing the outcomes of quantum events. However, this viewpoint is met with skepticism, as it introduces subjective elements into the scientific understanding of the universe. The relationship between consciousness and observation remains speculative and is a topic of ongoing exploration and debate in both scientific and philosophical circles. Quantum decoherence is a concept that seeks to address the apparent collapse of the wave function without invoking the need for conscious observers. It proposes that interactions with the external environment cause the quantum system to lose coherence and exhibit classical behavior. While quantum decoherence provides a plausible explanation for the transition from quantum to classical behavior, it does not entirely eliminate the role of observation. Instead, it emphasizes the importance of the broader environment in influencing the behavior of quantum systems. The challenges associated with studying quantum phenomena, particularly at the microscopic level, contribute to the ongoing mystery of observation in the quantum world. Quantum systems are notoriously delicate, And the act of measurement itself can introduce disturbances that complicate the interpretation of results. Advancements in technology and experimental techniques continue to push the boundaries of our understanding of quantum observation. Quantum computers, for example, are designed to manipulate and measure quantum states, offering new avenues for exploring the intricacies of quantum behavior. As technology progresses, researchers hope to gain deeper insights into the nature of observation and its impact on quantum systems.